Are you 12? This is our 5th lesson for the topic of complex numbers. In this lesson, we're going to look at powers and roots. And in particular, we're going to be looking at mod-arg form and de Moivre's theorem because they provide a convenient way to calculate positive and negative integral powers of a complex number. So for example, we might want to express 1 plus I root 3 all to the power of 4 in Cartesian form. Now, of course, one way you can do that is just to expand that out using the binomial theorem, but there is another way. Instead of expanding it, we could write it in mod-arg form. Now remember, that means that R, which is the modulus, is going to be the square root of 1 squared plus root 3 all squared, which is 2. And our argument, theta, is going to be inverse tan of root 3 over 1, which is pi on 3. So instead of 1 plus I root 3, we're going to write 2 cis pi on 3. So let's do that to the power of 4. So z to the power of 4, this is going to be 2 to the power of 4. And de Moivre's theorem says that we're going to bring that 4 down in front of the argument here. So it's going to become 4 pi on 3. Now if we want to go into Cartesian form, we're just going to expand this out and use exact values. And tidying it up, we end up with negative 8, take away 8 root 3i. So let's quickly review the first method we used for finding the square roots. Let's find the square roots of 1 minus root 3i. So we're going to let 1 minus root 3i equal a plus bi all squared, expanding that right-hand side out and equating real and imaginary parts, we get these two equations. Now for this second one here, let's make b the subject. Now we're going to substitute it in here. So we're doing simultaneous equations. So it gives us negative root 3 on 2b all squared. Take b squared is equal to 1. Square top and bottom, and we get 3 on 4b squared. Take b squared is equal to 1. And now I'm going to take this 4b squared and multiply every single term by that. So I get 3 take away 4b to the power of 4 is equal to 4b squared. And I'm going to move these two terms over this side so the b to the power of 4 term is positive. 4b to the power of 4 plus 4b squared take 3 equals 0. Factorise. And we're going to end up with b squared is equal to either negative 3 on 2, which it can't be equal to, or a half. So taking the square roots of both sides, we end up with b is equal to plus or minus 1 on root 2. If I rationalise the denominator, we have plus or minus root 2 on 2. Now we also need to know what a is, and I'm actually going to substitute in this version of b, so I end up with the square root on the top. So a is equal to negative root 3 divided by 2 on root 2, and I've taken the plus or minus here. Now because I've got this negative here, it's going to flip this plus or minus upside down, if that makes sense. So I end up with minus or plus root 6 on 2. So putting it all together, our square roots are negative root 6 on 2 plus root 2 on 2i, and root 6 on 2 take away root 2 on 2i. Now let's look at an alternate method, and this method is going to be good for all roots. Let z squared equal 1 minus root 3i. We're going to change this into mod-arg form. It is 2 cis of negative pi on 3. Now z is going to be equal to r cis theta, so let's substitute that in. So we've got r cis theta all squared is equal to 2 cis negative pi on 3. Using de Moivre's theorem, we have r squared cis 2 theta is equal to 2 cis negative pi on 3. Now we're going to equate the arguments and the moduluses. R is obviously root 2, and 2 theta is going to be equal to negative pi on 3 plus 2k pi for k is equal to 0 or 1. Now just simplifying that equation involving theta, we have theta is equal to negative pi on 6 plus k pi for k is equal to 0 or 1. And now all we do is substitute in k is equal to 0 and work out those exact values. And we have one of the roots. And then we substitute in k is equal to 1 and we'll find the other one. So what about roots other than square roots? Now right at the beginning of the video we looked at this question, 1 plus root 3i all to the power of 4. When we expanded that all out we got negative 8 take away 8 root 3i. So we can say that 1 plus root 3i is a quarter root of this complex number. But what about the other ones? This is actually not a viable method for us finding the roots of a complex number. So instead we're going to use that second method that I showed you with the square roots. Here's an example. Find the values of z for which z to the power of 6 is equal to 64. Now obviously plus or minus 2 are two of the solutions, but we learnt last lesson that there aren't only two. Any polynomial of degree n has exactly n zeros. So this one has 6. How do we find them all? Let's start by letting z equal r cis theta. And we're going to substitute that into here. We get r to the power of 6, cis 6 theta is equal to 64. But 64 is equal to 64 cis 0. So let's put 64 cis 0 on this side. Now we're going to equate moduluses and arguments. R is obviously 2, and 6 theta will be equal to 0 plus 2k pi for k equals 0, plus or minus 1, plus or minus 2, and 3. And then dividing through by 6, we end up with 0 plus k pi on 3 for k is equal to 0, plus or minus 1, plus or minus 2, and 3. And so we know that z is going to be equal to 2 cis k pi on 3. Now let's just work through the different values of k. So when k is equal to 0, first root is 2. When k is equal to 1, z2 will be 1 plus root 3i. When k is equal to negative 1, our third root will be 1 minus root 3i. When k is equal to 2, our fourth root is negative 1 plus root 3i. When k is equal to negative 2, our fifth root is negative 1 minus root 3i. And when k is equal to 3, our sixth root is negative 2. So altogether, the roots are plus or minus 2, plus or minus 1 plus root 3i, and plus or minus 1 minus root 3i. Now on an Argand diagram, those complex numbers are going to form the vertices of a regular polygon. In this case, a hexagon, because we had z to the power of 6 equals 64. And the angle between those complex numbers is pi on 3. Here's a past exam question. Part 1. Find all the fifth roots of negative 1 in modulus argument form. In other words, solve z to the power of 5 is equal to negative 1. Now, remember, we want to put this in mod arg form here. And we know that 1 cis pi is going to be equal to negative 1. So I'm going to make that negative 1 into 1 cis pi. We're going to let z equal r cis theta, and so substituting that in here, we're going to get r to the power of 5 cis 5 theta is equal to 1 cis pi. Equating the moduluses and the arguments, we get r is equal to 1, and 5 theta is equal to pi plus 2k pi for k is equal to 0 plus or minus 1 plus or minus 2. Dividing through by 5, theta is equal to pi over 5 plus 2k pi over 5 for k equals 0 plus or minus 1 plus or minus 2. So putting that together, we have z is equal to cis pi on 5 plus 2k pi on 5. Let's substitute in k is equal to 0. Our first root is going to be cis pi on 5. When we substitute in k equals 1, we get our second root is cis 3 pi on 5. Substituting in k equals negative 1, our third root will be cis of negative pi on 5. When k is equal to 2, the fourth root is cis pi, which is negative 1. And when k is equal to negative 2, the fifth root is cis negative 3 pi on 5. And so our roots are negative 1, cis plus or minus pi on 5, cis plus or minus 3 pi on 5. And you can see how the roots are occurring in conjugate pairs. Now, the second part of that question was to display the roots graphically on an Argand diagram. I've drawn this on GeoGebra. You'll of course have to draw it by hand. But here we can see, here's the root, z1 is equal to -1. These two are cis plus or minus pi on 5, and these two are cis plus or minus 3 pi on 5. And the angles in between these vectors, they're all going to be the same. In fact, they'll be 360 divided by 5, or 72 degrees, or in radians, 2 pi on 5. Now let's look at some shortcuts for writing in modarg form. If you've got a polynomial that's equal to 1, then you're going to let that equal cis 0. If it's equal to -1, the way to get -1 in modarg form is cis pi. If it's equal to I, we're going to put that equal to cis pi on 2. And negative I, it's going to be cis of negative pi on 2. Now you might be wondering, can we use exponential form to find complex roots? And yes, we can. So let's do that with this question. Z cubed is equal to I. Now instead of writing Z equals R cis theta, we're going to write it as R e to the I theta. And substituting it back into that equation and writing I in exponential form, we can now equate moduluses and arguments. So R is obviously equal to 1, and 3 theta is going to be equal to pi on 2 plus 2k pi, for k is equal to 0 or plus or minus 1. And dividing through by 3, theta is equal to pi on 6 plus 2k pi all over 3. Okay, we'll start by substituting in k is equal to 0. Theta 1 will be pi on 6. Substituting in k is equal to 1, theta 2 will equal pi on 6 plus 2 pi on 3, which is 5 pi on 6. And then substituting in k equals -1, we get pi on 6, take away 2 pi on 3, which is negative pi on 2. And so the roots are e to the pi on 6i, e to the 5 pi on 6i, and e to the negative pi on 2i. Or in Cartesian form, they are a half outside of root 3 plus I, a half outside of negative root 3 plus I, and negative I. Let's move on to complex roots of unity. Now, exactly the same maths, except we're only interested in equations of this form. So roots of unity, because we're going to have a 1 here. Now the good thing about this is there's going to be a lot of shortcuts that you can use. So there are going to be n roots, just like before. They are going to be equally spaced around the unit circle, separated by an angle of 2 pi on n. The roots can be written as 1 alpha, alpha squared, alpha cubed, all the way up to alpha to the n minus 1, and 1 will always be one of the roots. The roots are going to occur in conjugate pairs, and they're going to form the vertices of a regular polygon. And as the vector sum is 0, the sum of the roots is always going to be 0. You may also get asked about the product of the roots, and that's going to be equal to -1 to the power of n plus 1. I said before that there are shortcuts that you can use, and on this slide I've got some tips and some hints, because some of the questions can get really, really tricky. So with complex roots of unity, z multiplied by its conjugate is always equal to 1. It's really useful. These two you should already know. Z plus its conjugate equals 2 cos theta. Z minus its conjugate equals 2i sine theta. Cos is even, sine is odd. We use that all the time. These two, from angles of any magnitude, cos theta is equal to cos of 2 pi minus theta, and cos theta is equal to negative cos of pi minus theta. And this factorization could come in handy. Basically, if you have anything that looks like this, it's going to be equal to z, take away 1, and then the addition of all of the rest of them down to 1. So expand that out, say for a cubic, and make sure it makes sense to you. So let's look at an example. Find the complex roots of z to the power of 7 is equal to 1. So we'll start off the same way. Z to the 7 is equal to cis 0. And cis 7 theta will equal cis 0, since we know that r is going to be equal to 1. So 7 theta will be equal to 0 plus 2k pi for k is equal to 0, plus or minus 1, plus or minus 2, plus or minus 3. Dividing through by 7, theta is going to be equal to 2k pi on 7. And so the roots are 1, cis plus or minus 2 pi on 7, cis plus or minus 4 pi on 7, cis plus or minus 6 pi on 7. We show that cos 2 pi on 7 take away cos 3 pi on 7 take away cos pi on 7 is equal to negative a half. Now, this is to do with the sum of the roots. If you had them all multiplied together, all those causes, it would be to do with the product of the roots. So we're going to start with the sum of the roots. So it comes from the fact that the sum of the roots is equal to 0. Here are our roots, so let's add them all up and put them equal to 0. Now we're going to use z plus the conjugate is equal to 2 cos theta because here I've got conjugates, here I've got conjugates, and here I have conjugates. So from these two, we end up with 2 cos 2 pi on 7. From these two, 2 cos 4 pi on 7. And from these two, 2 cos 6 pi on 7. Taking the 1 over the other side and then dividing by 2, we end up with cos 2 pi on 7 plus cos 4 pi on 7 plus cos 6 pi on 7 is equal to negative a half. Have a look at where we're going. We just want to change these two. And we can see that these two here are supplementary angles. So since cos theta is equal to negative cos of pi minus theta, cos 2 pi on 7 take away cos 3 pi on 7, take away cos of pi on 7 is equal to negative a half. Okay, let's finish up with this question. Given that omega is a complex root of the equation x cubed is equal to 1, part 1 show that omega squared is also a root of this equation. So we know that omega cubed is going to be equal to 1. What we want to prove is that omega squared all cubed is also equal to 1. So let's start with omega squared all cubed. Well, that's the same as omega cubed all squared, isn't it? And we know omega cubed is equal to 1, so this is equal to 1. So therefore omega squared is a root of the equation. 2. Show that 1 plus omega squared is equal to 0. So this is the question that involves the factorization. We start by putting x equal to omega. So omega cubed is equal to 1. And so omega cubed take away 1 is equal to 0. Factorize. So we've got omega take away 1 and then all of the lesser powers added up. So we're just solving an equation here. The null factor law says either this is equal to 0 or this is equal to 0. And so 1 plus omega squared is equal to 0. 3. Hence simplify 1 minus omega squared, 1 minus omega to the power of 5, and 1 minus omega to the power of 7. All right, which is this. All right, what we're going to do is reduce these down because we know omega cubed is equal to 1. So this is the same as, instead of omega to the power of 5, it's omega cubed, omega squared, and instead of omega to the power of 7, it's omega to the power of 6 times omega. All right, that's equal to 1, and so is that. And so these are the same, aren't they? So we can join that all together and square it. And now I'm going to expand through these brackets, like this. Now we know that omega cubed is equal to 1. Now up here is what we proved in part 2. I'm going to make 1 the subject, and it's equal to negative omega take away omega squared, which is here. So this is equal to 1 plus 1 plus 1, all squared, which is 9. Okay, that's it. Our last lesson in this topic is about regions in a complex plane.